So actually, I posted the first lab assignment. The first lab assignment requires first lab assignment requires you to install model sim and simulate the very simple logic gate such as AND or OR gate. But due to United States regulations, so I found the downloading model sim is blocked recently. So actually we used the model sim simulator in the previous semester, but in the current semester, I think we cannot use the model sim. So actually I found the way to use the other version of the model sim for this course. So I revised the lab assignment 1 document, and then I will post the first lab assignment on Wednesday. So the 1 week is delayed. And in the previous class, we learned about the operands of the computer hardware instruction. So actually, these are the operands of RISC-V instructions. So the main topic of the, actually, you need to remember that we can use the operands, so we can use register data. That means the data stored in registers and immediate value as operands of the RISC-V instructions. So operands, so we can use the data in registers and can use the immediate values. Okay, so that's what we learned in the previous class. Then I mentioned that the registers are the very small memory, and then these registers are very fast, and then registers are indexed by the register numbers, that address. But these register numbers are very similar to in the address of the main memory, because with these register numbers, we can distinguish the various registers in the processor. And then immediate value is just the number. And then in the RISC-V instructions, we use the 2's complement number system. So with the 2's complement numbers, we use the MSB. So MSB is the rightmost bit of this number of binary numbers. So it's 가장 왼쪽에 있는 거죠. So we use this MSB bit as sign bit of 2's complement number. So you need to remember that we can use any plus number, minus number, and zeros as immediate values in RISC-V instructions, such as like this. So we can use any not any integer numbers actually, because there is a limitation. So that means that the maximum number and the minimum number of these immediate values are also this so there is the limitation of these maximum numbers or minimum numbers of these immediate values in the RISC-V instructions. Because we will learn in today's class, we will learn how to represent the RISC-V instructions into machine code. That means the binary code. And then in the binary code, the size of this instruction has the limited size. Also, this immediate value has the immediate limited field size. So that means the minimum and maximum numbers are also assigned to these immediate values. Okay, but usually we can use any plus numbers and minus numbers and zeros for these immediate values. Also, and then, so we briefly review the binary number systems. So I mentioned that we use the 2's complement number system for the immediate value. Actually, for the most of digital number systems, we use 2's complement number system, 2's complement binary numbers. So you need to know how to invert the sign of this 2's complement number. So how? If n is the n is a certain 2's complement binary number, then minus n equal is the negation of n and plus 1. So negation is the just inversion of each bit and plus 1. So so that is the actually the common sense of the binary number system. Actually, it's the number system. Okay. So that in today's class, we will learn how to represent the this RISC-V instructions as binary codes or machine codes. Also, we will learn about some additional instructions such as logic instructions and branch instructions of RISC-V ISA. Okay, so the first topic of today's class, not course. The first topic of today's class is representing instructions in the computer hardware. Okay, so until now we learned about the RISC-V instructions, but this instruction form is the assembly form. So what's that mean? So actually for programming we use the high-level language such as C, C++, or Python. So I repeatedly said that these high-level languages are very similar to our usual languages such as English. So we use the high-level languages. And then these high-level languages are translated into assembly codes. We frequently use the ASM for the abbreviation form of assembly code. So this high-level language is very similar to our usual language, like print, app, foo, hello world, and /n, just like this. And then this is the very complex function, but actually this high-level language statement or instructions are translated into assembly code. So assembly code use the instructions we learned in this course. So that means this assembly code use the instructions such as add, sub, load, and store double word. So that means the double word in RISC-V instructions. So then you can use the load word or store word. So actually we learned that these 4 RISC-V instructions. But as you can see, these assembly code use also English characters, right? So actually these are the human characters, human language characters. So, but I said the computer hardware can only understand the electric signal, binary electric signals. So it is the every digit of these machine code is composed of only 0 and 1. So what does that mean? This assembly code or assembly instructions should be translated into binary codes or machine code. It's called the machine codes. So and then machine codes only use the binary numbers like 0 and 1. So what does that mean? That R1, no, not X1, X2, X3. That is an example of add instruction of RISC-V ISA. So this instruction should be translated into some 0, 1, 0, 1, 0, 0, 1, 0, some machine code such like this. So in this class, we will learn how to translate these assembly instructions into binary codes. So what's the question?
Hi, is it common to see high-level languages translated straight to machine code, or does it usually go through assembly?
That's a very good question. So when you use the GNU compiler, like such as the GCC or some other compilers, so actually these high-level languages are firstly translated into the assembly code, and then this code is translated into the machine code. So, so if you use the GCC, so actually for the hardware, so we frequently use the C language for hardware research because C is developed for this Unix system or some operating systems. So when this high-level language is translated with the GCC compiler, then what files are generated? Object. So object files are generated. So you can find the .o files when the .c file is compiled. And then this .o, the object files are translated into the binary files. Such as, so if we do not specify any file name, then we can know that the a.out file is generated. So actually this this binary file includes the machine code, not assembly code. So actually the assembly code is can be generated, but this generated assembly code is not stored as the files usually. But if we add any option such as -a option for the GCC, then we can generate the assembly code. Okay, so that's a very good question. The firstly object code is generated, then usually the compiler generates this machine code or binary files directly. But if we specify any options, such as some specific options in the compile option, then we can generate the assembly files. Okay.
Thank you.
So as I explained, the instructions should be represented as the binary codes. And then these codes are also called the machine codes. So for example, add x1, x2, x3 should be represented some group of 0 and 1 binary numbers or binary codes. But this is the feature of RISC type ISA. So for the RISC-V, every instruction has fixed size. I mentioned fixed size. So what does that mean? If this is instruction is translated, then the translated machine code has a fixed size, such as 32-bit size. Also, the other instructions, such as load x1, 96, x22, then if these different instructions are translated into machine code, then this machine instructions also has the same size. That means 32-bit size. Okay. So, but that is a feature of RISC-ISA. RISC is the reduced instruction set computer. The CISC can be different. CISC, for the CISC type, such as x86, the instructions can have various lengths, such as 8-bit, 16-bit, or 32 bits. Okay, so this is the feature of RISC-V. But if you read the RISC-V specification, you can find some narrower instructions. So also you can find the narrow instructions in ARM instruction, ARM ISA, such as thumb. So ARM is also, ARM. ARM also has the fixed size instruction, like 32-bit instructions, but also ARM provide the 16-bit instructions called the thumb. But usually we, in this course, we learn only the fixed size instruction, like a 32-bit size instruction. Okay. So, so that means the instruction size is 32-bit. That means in byte, how many bytes? 32-bit is equal to 4 bytes. Okay. 1 byte is 8-bit. Because that means the instructions are represented as this 4-byte data. So I said it's a data. And then these instructions are also exist in memory. Okay. So so you may think that the RISC-V instructions, there are data transfer instructions such as load and store instructions. And then I said that, oh, these instructions only handles the data transfer between main memory and register file. But I also mentioned that, oh, instructions are also stored in memory as data form. And then also instruction has this fixed size. So that means that is the 4 byte. So that means the instruction has also, so you need to remember that. So if the data is stored in the memory, then this data need to have address. Okay. So that means the instructions are also accessed by this address. But you may be it may be confusing because I said so these data transfer or data movement should be only handled by the memory instructions. But instructions are also stored in the memory, and then these instructions are handled by hardware without any instruction. So I will explain about this later in the process architecture. Okay, but you need to remember that the instructions also have the binary form, and then these binary forms or binary data or binary code can be stored in the main memory, exist in the main memory. So first we will learn how to represent these instructions. But 32-bit is very wide. And then if we use the 32-bit binary numbers, then we need to write the 32-bit digit of these binary numbers. And then this will be very long. So we frequently use the hexadecimal code. The base 16 code is a hexadecimal. Then in short form, we use is a hex form. So with the hexadecimal form, we can use the 4-bit as one digit of hexadecimal form, such as this. So if we use the hexadecimal form, we can represent the 4 bits as one digit of this base 16 numbers. Then we can shrink the size of the number. Actually, the number count of the numbers, or number of numbers, number of digits, actually. So we frequently use the hexadecimal numbers. And then this slide summarized some different types, various types of RISC-V instructions. You can find the R-type instruction, I-type, S-type, and U-type instructions. And then I said RISC-V has the fixed sized instructions, 32-bit. So, and then this leftmost bit represent the MSB. Okay, and then MSB bit is the 31st bit. And then the LSB bit of the instruction is the 0th bit. Okay. So, and then in the example, I practically used this instruction. So that should be translated into the binary code. Which include 32 bits. So which information is required? So you can find that this instruction has several information. So the first information is the, so if we see that this instruction like add x1, x2, x3, then we can know that, this instruction, the required operation is add. So what is required? We need to represent add operation in this 32-bit binary code, right? And then x1 is the destination register numbers. We need to represent the destination register number, right? And then these two register numbers are source register numbers. We need to include the source register numbers, right? So that means in the 32-bit binary machine code, 32-bit binary machine instruction, these information should be included. And then, so this machine instruction can be split into the several fields. Okay. So one machine instruction is split, but it's divided into several fields. So these are called the field. Then in the plural, so there are several fields. Okay, and then these information like source register numbers are represented in a certain field. So that means a certain location of digit. Okay, So for example, this is the R type instruction. And then actually this add instruction is the R type instruction. It's called the R type. So if you see that this slide, you can find the RD, that is the destination register number. Okay, so that means this destination register number is represented in this field 11 down to 7 bit. Okay, so how many bits? 7 to 11, it's the 5 bits. So with this 5 bits, we can represent from 0 to 31, right? And then we learned that the number of registers, so it's the number of general purpose registers in RISC-V is 32, right? From X0 to X31. So with this 5-bit field, we can represent the destination register number. Okay, right? And then also you can find the RS1 and RS2. What does that mean? This RS1 is the source register number 1, like X2 here in this example, and the RS2 is the source register number 2. Also, these source register fields, source register number fields has 5-bit size respectively. Okay, so 5-bit 5 because there are 32 general purpose registers. So these we can represent these information in these 3 fields. Then remaining fields like function 7, function 3, and OP code. So using these 3 fields, we can represent the add. Okay, using these fields. Can you understand? So this is the R type instruction. Also, so there are some additional instruction types such as I, S, U type instructions. And then you can find several fields in these different type of instructions. So for example, the I type means this is the, as you, I means the immediate. So we can add the immediate values here, such as add I, X1, X2, and 4. So this is destination, this is a source register, and then this is immediate value. So immediate value is represented in this immediate field from 11 down to 0. So that means we can use the 12-digit 2's complement binary number for immediate values. Okay, I type, the S type, and U type. So there are several types. So what can we learn? So in this binary instruction, there are several fields, and then this is the instruction, the information of instructions are represented in the several different fields in the machine instruction. Okay, and then these rules are also defined in instruction set architecture. Okay, so because these rules are defined in instruction set architecture, the hardware engineer build this instruction decoder hardware promised in this instruction set architecture document. And then also if these instructions are received to the processor, then the hardware decoder analyze these binary instructions and then figure out which instructions are used and then which destination number, so what is the destination register number, and then what are source register numbers. So these are decoded in the binary instructions based on these instruction formats. Okay, so let's see the RISC-V R-type instruction. So as I explained, these R-type instructions have 3 register fields, RD, RS1, RS2, then the destination register number, source, and 2 source register numbers. So, and then as the RISC-V has 32 general purpose registers, these register number fields has 5-bit digits. Okay, and then there are function 7 fields, function 3 fields, and OP code field. Okay, then let's see how the instructions are encoded in the machine code. So these are encoded in the machine code. And then this process from assembly instruction to the machine instruction is called the encoding. And then the opposite direction is called the decoding. Okay, so let's see how the assembly instructions are encoded in the machine code. Okay, so it's an add x9, x20, x21. So this is the destination register number. So in binary number, it's 0, 1, 0, 0, 1, right? It's 9. And then the destination register number field is here. So it's a 9, maybe represented this number. And then source register numbers are the same. In the same way, it's x21, x20. So it's a RS1. It's a RS1. So it's a 20. This is RS2. So it's a 20 and 21. It can be represented as the binary numbers. And then add. So this add operation is defined by function 7, function 3, and OP code. So by using these 3 fields, we can represent the add operation. So 0, 0, 51. So here, here, here. So that is the 32-bit binary code. So this is with the binary numbers, then can be represented like this. And then with the hexadecimal code, and we can represent this machine instruction like this. Okay, it's simple. Okay. Okay. Or you can ask. You can say.
Remember that example from last lecture where you had like a constant in the function? It was like,
you mean immediate value, right?
Yeah, like a add I.
Yeah,
and
right.
You said constant 4 as one of the arguments. Could that number go over 5 bits?
Yeah. So I mentioned that in that case, we can use the I-type instruction. Okay.
Oh, okay, that's what you said. Okay.
So here, so we can use this immediate field, 12-bit immediate field. Okay.
Thank you.
Okay. So I share another. So can you use this Excel file, Excel sheet? So in this Excel sheet, I summarize the RISC-V instructions, but this is the IV32I. That means these instructions are the RISC-V 32-bit instructions, not 64-bit, but it's very similar. Okay. You can find some add instruction here, and then add I, solve instruction, then some different instructions. Also, we do not learn about the logical instructions, but you can understand. I believe you can easily understand that these logical instructions because this is the exclusive or and. This is a logical instruction. So you can find the load and store instruction and shift instructions, some such like that. But let's see the arithmetic instruction. So it's a R type instruction. Also, this is logical and shift instructions are also R type instructions. But this add I. So if we use the immediate instructions, then that is the I type instructions. So you can find the difference here. Add immediate, add yes. Also, in this Excel sheet, you can find the OP code. So OP code is the 7-bit field in the instruction code, binary instruction code. Also, you can find the function 3 field and the function 7 field here. Okay. Okay. Someone asked the question, so that's a very good question. So 어떤 거를 말하는 거죠? So you mean the so size? Do you mean this one? So 질문을 이해를 못 하겠는데 사이즈가 저 여기서 말하는 건가요? S type? Do you mean S type instruction or some other instructions? Okay, so I believe you the students mentioned that this S-type instruction like immediate 11 to 5 and then the immediate 4 to 0. So actually for the immediate instruction, the I-type instruction, the MSB 12 bits, so from 11 to 0, this field is used as the immediate, used for immediate values, okay? But the other type, like S-type instruction, so actually for the S-type instructions, we can also use the 12-bit immediate values, but these immediate values are split into the 2 parts, like we can use the 4 to 0 here and then 11 to 5 here. So that means this is the immediate value, and then immediate value actually has the 12 bits. So that means we can use the we can represent the minus 12 bit to so with these 12-bit immediate values, we can represent the minus 2 to 11. It's 11 to right. But For the I-type instruction, oh, sorry. Can you see this slide? Okay. 네, 처음부터 다시 할게요. So I think one student mentioned that this S-type instruction, because as in the S-type instruction, the immediate values are split into two parts, like immediate 4 to 0 and then immediate 11 to 5. But actually, the I-type instruction for most of the if we use the I-type instructions, such as I need to share the screen. Okay. I will share the screen here. So you can find this I-type instruction here, like load instruction and such as add I here and shift I instruction. So these are the example of the I-type instruction. But you can find the S-type instructions here, like store instructions. So actually I-type instructions and S-type instructions are both use immediate values. Okay, but for the I-type instruction, the immediate values are located from pin number 31 to pin number 20 of instruction code. So this is the instruction. It's the pin number 31 to 20. That is 12 bits, right? So these immediate values are assigned to this field, okay? But for the S-type instructions, these immediate values are split into two parts, like immediate 4 to 0 and immediate 11 to 5, right? But it's also 12-bit values, right? But these 11 to 5 are assigned to the, this is the I-type. The S-type, we assign the 25. We assign the first 5, 6, 7 bit, like immediate 11 to 5. To the instruction 30 pin number 32, 31 to 25. And then other part, immediate port 0 is assigned to the instruction 11 to 7. Okay. So these number represent the pin number of immediate values. Okay, 11 to 5. Also, these number represent the pin number of instruction, machine instruction or instruction code. Okay, so I said that instructions, RISC-V instructions is represented as the 32-bit machine instruction. So RISC-V RISC-V assembly instruction is represented as the 32-bit machine instruction. Okay, so that means this 32-bit machine instruction has bin numbers from 0 to 31. 그래서 32bit이죠. And then this bin number represents the location of the bit. Also, for the immediate value, we use the 12 bits. So that means immediate value can be represented the 11 down to 0. And then this represents how this immediate value is assigned to the bit location of machine instruction. Okay, so that means the 0th bit of immediate value is assigned to the 20th bit of machine instruction. Okay, the same. So 11 to 5. So 5 is assigned to the 25th bit of machine instruction. 설명이 됐나요? It's okay. So if you have further questions, then you can post your question on the piazza. 네. Okay. Okay, this is the I-type instructions, and then I already explained about this I-type instructions. In the actually this example add x1, x2, and 4. So in the I-type instruction, there is only one source register numbers, and then we have immediate values. And then I said it is immediate values represented as the 12-bit 2's complement number. So 12-bit 2's complement number. So in the instruction format, so we need the destination register number, source register number, and then immediate value. So these immediate values are assigned to the first bit number 31 to 20 of the instruction code. And then we can use the other fields such as OP code and then function 3 to represent the operation of the instruction. Okay. And then as you can see, the format of the different instruction format has the same location for the same field. So what does that mean? So for example, OP code are always assigned to the pin number 6 to 0. Okay, and then normally the destination register numbers are assigned to the pin numbers from 11 to 7. Okay, same RS1 and RS2 is the same. And if the RS2 is not used, then these locations are used for the immediate values. So that means the same information field is assigned to the same location in a single machine instruction. So if this same rule is applied, then we can make the simple hardware decoder. So that means this regularity makes the hardware simpler. Okay, that's also very important. 어디를 말하는 거죠? Where is the immediate? 어디 말하는 거죠? Oh, this one. This is the different. Yeah, okay. So actually, U-type has the different format usually. So actually, I will explain about the U-type later, but this U-type has some different format. So it's not immediate. It's not immediate format. Okay. So we use the S-type instruction for store instructions, and then for the store instruction, actually, if you see the store instruction like SW, X1, 96, X2, this is store word, and you can use the store double word because this is the 64-bit computers. So in the store instruction, this is the actually source instruction. Okay, it's the source register. And then this register is also kind of a source register because this register is used as the base address of array. So this data should be read from the register file. So that's why this X2 is also source register. And this 96 is the offset. So offset is actually immediate value. So for the store instructions use 2 source registers and 1 immediate value. Okay. So that's why S-type instruction is different from I-type instruction. So they use the 2 source registers, and then this S-type instructions do not use RD field. So it's the destination register number. But as the RS2 is used to some field of the immediate values are occupied by RS2. So the part of the immediate values are assigned to this RD location because RD is not used. That's why the immediate values are split into 2 parts, and then the LSB5 bits are stored in this RD location, originally RD location of the R-type instruction, and then other 7 bits are assigned to this field. Okay, it's very simple. And then this slide explains about the stored program computers someday. So actually, in the first, in the start of the class, I explained that instructions are also stored in the main memory as in the very similar form of the data. So this is the main memory. This actually our user data, such as A equal 1, B equal 2. This is the data we used in our program. So these user data are also stored in the main memory. And then that is obvious because we already know that data is stored in the main memory of the computer system. But instruction, how about the instruction? So we learned that computer instructions can be represented as the binary data, the binary format. So actually the A equal 1, this can be represented as the 0, 0, 0, 0, 2, 2, 2, 2, 2, 1. And 2 is the 0, 0, 0, 2, 2, 1, 0. So our user data also represented as the binary data or binary numbers. Instruction can be represented as the binary data. Also, our user data can be represented as the binary data. Actually, same. So these all instructions and our user data are also stored in the main memory. And then, as I mentioned, in order to access this data, we need the address. Okay, we need the address. So in order to access the instructions in the main memory, this address of instruction is defined in the computer processor, and then the computer processor we actually read the stored instruction from the main memory, and then the instructions are decoded in the computer hardware, and then computer hardware performs the defined operation. Okay. So we need the address of instruction. because instructions are also stored in the main memory. And then actually this address of instructions, addresses of instructions are called the program counters. Okay, so it's called the program counters. So actually the processor accesses the instructions in the main memory using program counters. Okay, so we will learn about these program counters later in the process architecture. So chapter 4. So, but you need to remember that instructions are also represented as the binary data. So instructions are also located in main memory of computer systems. Okay. And logical operation. So actually our data is represented as the binary data. So that means also if you took the digital system design, digital logic design, it's a digital logic design, then I believe you learned about some logical operations such as AND operation, OR operation, exclusive OR, NOT operation. So these are kind of logical instructions, like 1 and 1 equal 1, 1 and 0 is 0. So actually the computer's hardware handles the binary data. So that means computer hardware requires logical operations. So this slide shows the examples of logical operations like shift left, shift right, and bitwise AND, bitwise OR, exclusive OR, NOT. Also, we can use these operations in the high-level languages such as C and Java. So shift left means that just shift the location of the bit to the left by 1 bit, not by n bit, because shift left n. So in the C language, we can use this operator, like so it's the left direction. So for the shift right, we can use this operation. And then for the RISC-V, the equivalent instruction is the SLL and then SRL. And bitwise AND, we can use the AND and the OR bitwise exclusive OR, we can use the exclusive OR. But in the RISC-V, in the RISC-V, there is no NOT operation, but we can implement the NOT operation easily. Okay. Okay, let's see my Excel. Where is that session? Okay, let's see here. Okay, maybe we can find, you can see my Excel document. Oh, small. Oops. So as you can see, you can find this shift instructions like SLL, SLLI, SRL, SRLI, SRA. And so you can find the logical instructions. And then you can find the name and definition of the instructions. So there are R-type instructions and I-type instructions for the shift and logical instructions like exclusive or exclusive immediately. But you can find that some instructions have R-type and some instructions have I-type formats. Okay, but these formats are the same to all instructions. So that means if the R-type formats are applied to a certain instruction, then this instruction shares the same format. So that means the location of the destination registers and the source registers are the same, but which part is different? This part. Opcode function 3 and then function 7 parts are different. Okay. So it's a shift instruction. So just you can shift actually it's very easy. So shift SLM means the shift left logical. So it's the SLL, so shift logical, shift left logical, and then SRL means the shift right logical. So it's the just change the shift the bits to the left or right. But as you can see, the RISC-V has the also shift right arithmetic. So what does that mean? So actually two kinds of shift right operation, like SRL and SRA. So L means logical and RA means arithmetic. What is the difference? So difference means that, so this is the 1111, it's a 4-bit data. So if we shift to right 1, but shift to right logical, then that means this bit shift by one bit. So that means 111, and this bit LS bit is removed. And how about the MSB bit? This is the logical. So if you see the Excel code, then that is the just here. It means the MSB bit means the becomes the 0, just 0. But how about the SRA? So 1111, then that means we can think that this MSB bit of this number is signed bit, right? So if we shift to right by 1, that means it becomes the 111, but this MSB bit is replicated, so it becomes a 1. Why this is required? So this is the SRL and this is SRA, arithmetic and logical. What is the difference? If we apply the arithmetic shift, then we think the MSB bit is the sign bit. So for example, this, what's this number? Oh, how about 11102 here 0111 is the SRL, then 1111 is SRA. What is different? So this data can be -6 or -2, right? If the MSB bit is sign bit, then it should be -2. But if MSB bit is not a sign bit, then it should be 6. So shift right by 1 is usually equivalent to divide by 2, right? So if this number is 6, then it should becomes 3. But if this number is -2, it should becomes -1. So SRA is applied if the number has the sign bit. Okay. And then also we can apply this bitwise logical operation such as AND or exclusive OR. So that is the bitwise AND, bitwise OR, a bitwise exclusive OR. So that means the operation is applied bit by bit. So for example, this is the AND x9, x10, x11. So the bitwise AND operation is applied. So the result becomes the 0011. So here, and the OR is the same, exclusive OR is the same. Okay, I believe everyone knows about the definition of exclusive OR and. And then this slide shows the instruction summary of the RISC-V instructions here. So you can find this table in your textbook. So also I also summarized the definition of the instruction and type, and then code function 3 here, the Excel file. And you can find this Excel file on the Piazza. So these slides summarize the OP code of the instruction and then field of the instruction. So actually we just handle the R type and I type and S type instructions, but there are different type of instructions such as SB and UJ. It's a different type of instruction. So R type, I type, so load is here and store is here. Then some other instruction like add is here, add I is also here, I type. And then this SB type is used for branch instruction, and then some other instruction, and then U type is used for other instructions such as LUI. So if you see that this Excel file, you can find the SB type here, it's like branch instructions, and then UJ type is used for jump instruction. So I said that this immediate value has the different meaning. Okay. Let's see. Let's go back to so until now, we learned about the R-type instruction. This is the arithmetic instruction, and then logical instruction and shift instructions. Okay. And then we learned about the data transfer instructions such as load and store instruction. Now it's time to learn about the branch instruction. So this branch instruction is used for making decisions. So what is the example of decisions? So in the high-level language such as C, we frequently use the if condition and then do something, and then else do different thing, to 1, to 2. So that is the example of making decision. So what does that mean? These statements are called the condition state. 조건문이라고 하죠. In Korean, in Korean it's called the 조건문. So that means based on this condition, the executed instructions are different. So if this condition is true, then the computer execute this instruction number 1, and then if the decision is false, then it executes the instruction number 2. 6가 아니네요. 그죠? 4, 4, 2, 12죠. So these type of instructions are frequently found in our program. So the RISC-V instruction or computer hardware need to support these instruction types. So in order to support these instruction types, the computer, the RISC-V has the branch instruction. Okay, so this is the example of a branch instruction. So this is the BEQ. So BEQ means the branch if equal. And then this BEQ use the two source registers and then one target. So what does that mean? So this BEQ means that if the data in register source register 1 is equal to data in source register 2, so that is the condition. So and then condition is equal. Then if this condition is true, then jump to L1. That is the definition of BEQ. Then there are different instructions like B and E. So NE equal E means not equal. So that is here. So that means the conditions are different, but the formats are the same. You can find the various branch instructions here. So BQ, BNE, BLT, BGE. Also, you can find the meaning of the branch instruction here. If equal, not equal, less than, greater or equal. And then both formats are the same, like BQ, RS1, RS2, immediate. BNE, RS1, RS2, immediate. Because all branch instructions use the SB domain. Then what is this target? What is target? So that is the example of condition instruction. So if you see this program snippet, and if you see this code snippet, you can find that based on the result of the condition, different instructions are executed. Instruction number 1 and instruction number 2. But I mentioned that instructions are also represented as data. Okay, so that means instructions are stored in the main memory, and then every instruction is pointed by address, and then this address is called program counter. So that means this is the main memory, instruction memory. So all instruction, the instruction number 1 is stored here, and then instruction number 2 is stored here, and then different memory. These instructions have different addresses. That means different program counter values. So what does that mean? Target means the program counter of where? 1번이야, 2번이야. 1 or 2. Number 1 or number 2? Right, number 1. Because by definition, this I said by definition, if this condition is true, then the computer processor jump to target. So that means if this condition is true, then instruction number 1 is executed. So that means L1 is the program count of instruction number 1. Okay, by definition. So that's right. Good. So that is the example of a branch instruction, or this is also called the conditional operations. Okay, so this slide shows the example of these conditional instructions. So actually, the computer processor does these conditional branch instructions are very critical for the performance of the computer system. Also, these instructions are very important because we can make very complex application using these conditional instructions or conditional operations. So the computer hardware also support these conditional branch instructions, and then we will learn about these instructions in the next class. So I hope I could complete these conditional instructions in the today's class, but it is right. So I will stop here. So do you have any questions? Okay, do you have any further questions? Then you can post the questions on the Piazza. And, okay, and then thank you for listening, and then see you on Wednesday.